senior security advisor who knows how to test information technology in DEVOPS. Please welcome the co-founder of Silverskin Information Security, Mr. Jani Kirmanen. Welcome.
Hello. My name is Jani Kirmanen, and nice magic tricks, by the way. I'll just briefly tell what we do at Silverskin. Because we are a cyber attack company, not cyber security company. And this is, many people cannot understand what this means. But we believe that offense informs defense. So by only understanding how the attacker works can you build defense systems. If you only think in defense terms, well, then you end up having some crappy systems, which we have seen many times. What we do, well, basically, today's talk is mostly about cyber risk management, how to manage risk in software development projects or systems or processes, and how offensive operations relate to them. But the other thing is that this will be a joint presentation with my friend Parviainen, who will continue after my presentation. We'll do a quick context switch in the middle. So I'll start off with the high context. I tell you about the concept, and then Lisa can tell you about some practical implementation issues and findings and experiences with these concepts. But basically, whenever we do a security assessment, we do penetration testings, we do security audits, we help out people who do software development, we do train software developers to understand more how to test security, how to design secure software. And well, basically these are the principle for building insecure software. Basically you start off writing something nobody else can understand, then you Google for best practices, you just download a bunch of libraries and software frameworks without really understanding what they are doing. And lastly, you don't test anything. I'll present you two things only today. I present you two principles for securing operations. For securing, okay, I'm getting double mic'd here. And please understand, I tend to walk around the room. So anyway, the first principle of the two is that if you don't know what you have, you cannot secure it. This really relates to any kind of operations. It works in any system. You can take an organization to be a system of systems. But you really cannot secure anything if you don't really know what it all entails. And in the previous world where you did the development work first and then you removed the final product or final to the operations, you had to split in how the security has been built and how it will be maintained. And it's really hard to maintain something without proper documentation. And I have never seen a good security documentation about any information system. Because all developers know that writing documentation is really boring and it's only done to satisfy some vague requirement that we have to have some kind of documentation. But security documentation, well, what can it be? So here is a high-level concept of what kind of things or aspect is interesting in maintaining and also in developing information security. I'll walk you through this slide. So first off, we need to understand if there are security requirements. And these security requirements are external. Let's say if you are building a system which handles patient or health information, well, there are some laws and regulations which require you to do certain stuff. How do you handle the information? How do you protect privacy, and so on. Then you may need to classify some of the data or information being stored, and maybe there are some audit requirements as well. These are quite high level, but if we think about the technical system, any system contains information in some form. Well, you should just write that down. Functionality, what kind of functionality it provides to the users, and users can of course be humans or some other systems. So we need to understand what are all the interfaces the system has. What other systems are connected to our system, and which other systems our system connects to. And of course, what the data flows in between, how systems are authenticated, how authorization information and such things are implemented. And you, of course, should somehow describe what the technology behind the system is. And nowadays, you get really, if you're coding with modern tools, you basically know immediately what other libraries and dependencies you have. There's mostly dependency analysis. But you still have to know what versions you are using. Do you have a mechanism for spotting whether there are some vulnerabilities in the libraries you are using? So you need to maintain some kind of process which informs you if there are new discovered vulnerabilities in any of your third-party software. Because cybersecurity is mostly about securing connections between systems, and humans and technical systems are both systems. So we have a lot of interconnected systems, and this is where the complexity begins. It is really hard to understand what are all the systems that are connected without, if you do not list them. When we have done reviews, when we conduct product security reviews, it is very, very common that when we start interviewing the developers, that, well, what are the systems your system is connected to? First answer is, well, not really to anything. But when we continue asking and interrogating almost, we do have the Salesforce integration. Of course, our licensing system is external. And of course, there's this payment interface we are using. So it may first seem like there are no other systems, but when we start asking the developer, well, then at some point he'll remember that, oh we do have this one connected system. But if we do not document that anywhere, we have to rely on the developer's mindset and what he knows about the system. And if it's a complex system, no one person knows all the interconnected systems. Of course, developers and sysadmins are part of the equation. Because, those are the guys who have privileged access. And if we think about or talk about cyber attacks, it is not only the technical system we are interested in. We mainly target the weakest link. And the weakest link can be a sysadmin that opens every email that is being sent to you. So we need to understand who are responsible for developing and maintaining the system. And lastly, we need to understand who are the expected users for this system we're talking about. So bear in mind, this is a really high-level concept, but this is all part of the security documentation. We need to know, not precisely, but we need to know per system how they interrelate to each other. And, of course, all of this is basically documentation that is technical in nature and doesn't really have a security focus as such. But these are all needed in order to develop these three So in order to secure systems, we need to have a good understanding what the attack surface is. We need to have a threat model to understand what could go wrong and how. And well, where a threat model may sound like a fancy word or fancy term, misuse cases or abuse cases are really down to earth. What else the system could do than what it has been designed for? That is basically hacking, doing something that isn't supposed to happen. Related to interfaces, interconnected systems, end users, and so on, we have these basic security mechanisms or security measures like authentication, authorization, audit logging. How are those being implemented? Is there an external system that does authentication? Is there an external system for doing authorization and so on? So security documentation is all about putting all these connections in one place where one can understand how the authentication, how user access management, how user identity management has been implemented in the system. And you can take a single system and do the documentation, but typically you have many systems that can be in different networks. So we need to understand also how those authentication mechanisms work over network and how the connections are being protected, what the protocols are. So basically, understanding what could have security related or what could be security related and just writing it down into a document format of your own choice. So that is knowing what you have. Then when you go on to the next principle, which is offense-informed defense. So in the previous slide, there are two like threat modeling and abuse cases. Well, those are our concept of what the attacker could do. We are trying to become the attacker when we do threat modeling and when we do abuse case modeling. So we try to understand what could be valuable to an attacker in our system, and then we build the security mechanisms. But then we need to somehow evaluate how effective our mechanisms are. So this is where the security testing kicks in. And basically, if we think about software development processes, in the old days, people designed something first, implemented next, and then tested whether it worked. But that testing isn't about proving something works. It is about finding defects, finding something that's not working. And the tricky thing about security is that security vulnerabilities are typically the case where the code does not exist. That's why you have a security hole. There should be something in it, but there isn't. But if you think about unit tests mainly test what you have. So there's some kind of conflict here. So how can we test for something that isn't there? Well, that's why we are here. So basically, security testing can be divided into two different categories. In the first case, we try to find the security we try to discover the security defects. Most of you have heard about vulnerability scanning. Well, what does it entail? Well, basically, that can be a fingerprint of the system, and we just look up to a vulnerability database to see if we are running any vulnerable third-party component. There's nothing magical in it. Fast testing, on the other hand, could be considered quite magical. It is basically sending garbage into a protocol implementation to see whether the input validation mechanism, first of all, exists at all, second of all, works properly. And then we have the penetration testing, which takes the whole system, included with the human components and network components and infrastructure, and then the application code. So there are differences in the scope. So fast testing can pinpoint only to, let's say, one protocol implementation. And well, the penetration testing involves everything. Testing out logic flows, testing out abuse cases, stress testing, maybe even denial of service attacks. But these are ways of finding bugs you didn't know you had. So penetration testing can reveal that, hey, we should have a security mechanism, we didn't even design for it, or we do have a security mechanism, but it doesn't work in all cases. Or we do have a working security mechanism, but we have somehow configured it wrong. We have forgotten to turn the key, although we have a lock. So once you have found the security defects, well, then you go and fix them. And then you can build security regression after we have fixed them. So now we do have the unit test, but we cannot discover bugs in a way. So with my last slide before this gets shared. So compared to waterfall methods, one of the benefits of using agile approach is a better coping with change. And in our model, we start with the change analysis. Let's say if we are adding a new feature to the system, we try to understand how our system is going to change. If the new feature involves storing, let's say, new kind of data, we have to understand whether there are some external requirements to the data. Do we have to take special care of, let's say, some person information? Because we do have a threat model, we try to see whether the threat model is updated due to the feature changes. It could be a new mechanism that, let's say, we're building a patient or health information system, and we have this new feature that will the doctor can open any patient's record up. But then we discover this kind of abuse case that, well, if someone were able to hack or somehow hijack, let's say, the doctor's session, the attacker could, let's say, go through every patient's information. Because, well, the doctor has access to everyone's information, but the attacker could abuse that privileged access somehow. So we spot that, well, we need a new mechanism. Our controls are not sufficient. So we have to, let's say, add a new feature that we can limit the number of records the doctor can view daily. So we extend the existing controls, and then we try to review how the system has now changed, and we can write a test for it, and then we're back to the change analysis again. This is due to the fact that penetration testing, although we would like in a way to conduct penetration tests after each and every change to the system, because every change could potentially cause some new weakness or introduce a new weakness in the system. It is bloody expensive. It takes many days, and if the change has been really small, well, it's not good return for investment. So we try to use review and other kinds of testing methodology in any of those flaws that could be introduced. We try to understand what we have. But we are still conducting penetration testing periodically or after major changes. Because, well, the nature of software is that it is complex, and complexity is hard to understand. And if you don't understand what you have, well, then there may be some hidden feature in what you thought was secure. So we need to bring in other people to test our software. So I'm telling that even developers can write their own test, but of course nobody wants to find bugs in our own software, that's a fact. So we need to have other people doing the penetration testing. But we need to keep this lean and light. So this is a lot lighter version. And we are conducting penetration testing periodically. Typically, in a typical, in contrast, a typical software product from our point of view is that you have done something and you are deploying it, and before you are deploying something, you need to assure that does it have any. Is it secure to take into the production? But if there's only one test happening before taking it to production, well, that's not enough. So you need to do security testing during development, not only after it's been done in a way. Okay, let's see what we have. So basically, two points here is to understand your system thoroughly, to understand what are the selected security mechanisms, or let's say security measures, but then you have to measure the security by testing it, and testing it all the time. And understanding that after it's into production, of course, the DevOps is different approach, where you are really creating the production environment all the time, so you will have this gap in the test and production in a way. But nonetheless, the security model is always changing because the world is changing. The attacker methods are changing. There are new flaws discovered in every piece of software all the time. So you need to not only care about your own code, but the infrastructure. But how to do that? We have Visa to tell about your experiences about how to make it automated. Thanks.
Thank you, Jani. Can everybody hear me okay? I think yes, because my voice sounds really loud. Okay, so my name is Visa, and as you may have guessed from the kind of changing scenery around here, I work for Eficode, and we've been talking about this subject with Jani before, and we'll probably be talking about it together again. And basically, what I'm going to talk to you about is a little bit of practical advice on how to actually do the early test often part of security testing. And more specifically, I'll be introducing a way to split an application architecture into a little bit smaller pieces in such a way that it will help designing tests and recognizing what you can test. Then we'll go through each of these categories and look what can we automate and maybe what limitations we have. And then I'm going to show a really practical way and like going into details about which tools you should use or could use in a typical case. But what I'm going to show you is a kind of basic version of a simple software security testing system. There is a lot of complexity here that you can add. But how many are actually doing automatic security testing right now? Hands up. There are maybe 2 or 3 people. Okay, so yeah, probably it's better to start with the basics and then go into more advanced stuff later on. But I'm going to today just introduce the basics. First one assumption. I will be kind of assuming that we're dealing with a kind of standard web application with a load balancer, a bunch of atoms, some kind of storage system, and maybe a clustered database system. If you're doing something that's really a lot more complicated than this, you will have to think a little bit more thoroughly about what you do and how you test it, because complexity introduces more potential security flaws. So but 99.9% of web applications are about this complexity level or less complicated than this one. So we should be fine, but just keep in mind, I'm going to give you kind of rules of thumb, and if you're doing something a lot more complex, you need to think about it. Okay, here is a way to structure or kind of look at an application's structure in a simple way. There's of course other ways to do it, but this helps our thinking in terms of security testing. So first we have infrastructure, which consists of things like the servers, the databases, and any network elements, and all of the kind of application software running on the server, like the web server itself, which isn't a part of your application, but is kind of required infrastructure for it. And then we have application structures themselves, which are like frameworks and the libraries that the application uses. And then we have the application logic, which is kind of the actual use context and the purpose of the application and what it actually does and what's its benefit to the user. And each of these categories have a couple of ways in which they can ruin your day very royally. And in infrastructure, we have known weaknesses. And of course, we also have unknown weaknesses, but there's very little we can do about those short of actually auditing every single piece of software in your application stack. We're going to just ignore them for now. There's very little we can automatically do about them, but what we can do about is the known weaknesses, so we will concentrate on those. And known weaknesses, of course, are things that are usually found by others and then informed in some kind of case. Then we have configuration errors. Jani already mentioned you can just simply misconfigure an otherwise perfectly good piece of software and it will misbehave and cause some kind of security error. This can mean something like a low security password, or somebody forgets to turn HTTPS on, or something like this. Then in the application structure, again, we can have known weaknesses. Same thing as well. Then we have this kind of a little bit weird box here, communication handling errors. Sounds pretty abstract, is pretty abstract, but it encompasses things like session handling and input sanitation. So kind of how the system communicates with external parties, whether those are users or some kind of external system. Finally, in application logic, we have things called state transition errors. And a state transition error is something like within the context of the application, it does something that it shouldn't do. So maybe in a web shop there is a way for me as an end user to cause the web shop to price a nice, normally €1,500 bicycle as a €1 bicycle and order it. Basically, it's kind of it's only incorrect in the context of the application, right? But it could be correct in some other context, maybe. And then usage errors are kind of also about application logic security errors, and it's a little bit different from what I just described. Again, let's use bicycles and web shops as an example. But basically, for example, in an ERP system, there is often something called price list, which determines the prices for everything. And if somebody changes the price list to another and forgets to set all of the prices for every product, and we end up having €1 price as a default price for the bicycles, and then I'm going to order 1,000 bicycles for myself, that's a usage error. But still a security error because it causes a kind of unexpected security issue as a result of the user's actions. Good. Let's take a look quickly on what we can do about this. So, known weaknesses we can find with a vulnerability scanner and with version management. This is getting better if you have proper DEVOPS in place. You will probably have automatic installation of different software components. You can find a list of things and their versions in a centralized place without looking everything up. So version management helps here. Configuration errors, network scanner, you can kind of minimize the attack surface so that you can make sure that there's no weird crap running on your server and weird services that aren't supposed to be there. The same goes again with vulnerability scanner. Many scanners can detect if you're missing some kind of key configuration parameter or something. All right, moving swiftly along. Application structure, again, known weaknesses. Static analysis can usually reveal deprecated components, but you can't really trust that. Again, version management raises its head. Why is it not enough to just use static analysis? Because in these vulnerability scanners and static analysis libraries, you don't always immediately get all of the new vulnerabilities in play, so you will have to probably cross-check your version lists and possible email from security-related mailing lists or something like that. Then again, communication handling errors. Static analysis can help here to an extent, but not exclusively, especially input sanitation errors are pretty easy to find, especially if you're using tools that came with your framework. Rails, for example, has Brakeman, which is very nice, and can usually detect input sanitation and input handling errors. An attack proxy, this is the type of fuzz testing that Jani was mentioning. Attack proxies are great, but they can usually break your application. But that's provided that you're using them correctly. I'll come to how to use them nicely in a minute. But you will generally also need code reviews because there is a chance that something is missed, and the second pair of eyes will help you a lot. You all know why you need to do code reviews. It's because you become blind to your own code after you've been staring for a while. Good. Finally, application logic. You notice now that these gray boxes are increasing. The gray box means that there is no way to sensibly automate this thing at this point in time, and that will remain so for the most of these gray boxes for as long as humans are smarter than computers. This is because attacking an information system is a creative art rather than an exact science. So, as we say at Eficode, what you can document, you can automate, and you can't really exhaustively document ways to attack against an information system. So here we have manual testing, which basically means things like penetration testing. It requires somebody to think that what could I do here that could cause this system to go into an illegal state, so to speak. In usage error, this becomes much more difficult. You of course can do things like optimize your processes and make sure that you're giving all of the information to the user, but that's more security-centric user interface design than anything else, and it's very hard to automate. It still requires somebody to think about things very thoroughly. And then, of course, again, manual testing. And you notice here we do have acceptance testing as a blue box. You can detect state transition errors, but as Jani pointed out, automatic testing tests against regressions, except during TDD or DDD, but you still need to have accounted for these security scenarios in your test. So some human has thought about this and written down a test. So you can't kind of acceptance test security in an exploratory way. So that's kind of the key thing here. Let's look at the whole thing just for a minute here. So actually, quite a lot of stuff we can automatically test, but there are things which you can't, as we discussed. I'm not going to go into kind of social and psychological aspects of operational security, but it's very important. You need to think about that. And it all starts from having proper security requirements, threat models, and I think you should integrate your security into your acceptance criteria so that somebody thinks about these things for every single ticket that goes through your pipeline. This is very important. Like if you remember one thing, remember this. Like somebody needs to think about these things. I don't really have time about how you actually do it, but this is the way. Okay, let's take a look at how to integrate. I promise you will be at lunch on time. This won't take very long anymore. How many of you know what continuous integration or CI server is? Hands up. Okay, basically all of you. This is great. This is great. More often than not, there's like half of the people who don't know, but maybe it's kind of the crew at the event called DEVOPS 2016. We tend to know these kinds of things. All right. So I'm in favor of this kind of dualistic approach where we have a CI run and a human code review running in parallel, and the CI will vote similar to the humans whether this is okay or not. I have arranged these boxes here in such a way that we'll start with the stuff that goes through fast and is likely to to reveal catastrophically important, like there's some kind of algorithm that has stopped working, catastrophically important defects in the application, and that return their results very quickly. Things like unit testing are here. And then we move on to static analysis and infrastructure scanners and attack proxy because those things are less likely to kind of reveal catastrophic problems in the application. They're also a little bit more fuzzy, and I'll come into this in a moment. So they may give you false positives, and they take a little bit more time to run. So you want to give your developer or yourself the feedback about what he's doing or she's doing very quickly, and especially when it's very important for you. But this is very simple. You can do this with, for example, Jenkins. And sometimes, of course, you can run these things in parallel. That's great. And as Steve pointed out, that it's very cheap to get more machines, but it's kind of expensive to get more consultants. So if you can solve these things with more processing power, it's probably worth it. So, okay. I'll promise to name a few tools. I will just say a few words about them. So there are really many security testing tools on the market right now. Many of them are free, many of them are really great, but the problem is that not very many of them actually integrate with CI very well. And this is a problem because, of course, you want to have kind of a centralized pipeline for this. But I will name a few that are very good and kind of can get you, I think, the most benefits of automatic security testing with a relatively little effort and also capital investment because these are pretty good. First, ZAC, attack proxy. It's very easy to use, and basically what it does is fast tests your interfaces and communication with your servers. And what you do is basically you kind of give it an example of communication with the server, and then it will try to take that communication and turn it into some kind of evil things. This will really great benefit from browser-based automatic tests because you can basically run those through the ZAP to give it an example of all the possible integrations. And it has a Jani plugin, so you will be able to integrate it into your workflow. Very good. Another thing is SonarQube, which is a static code analysis platform. I know that there are some people here who are actually using this also. And it does also integrate with Jenkins. It has a very good language support, and most importantly, it has pretty good security libraries. CWE, Common Vulnerability Enumeration. It's a bit big, probably not worth running through all of that. SANS 25 is kind of a subset of CWE. Definitely worth running. It's kind of like most likely most critical security problems in one page. And OS Top 10 is another good list. There is some overlap between these two guys, but they do have a kind of slightly different approach to security. Worth running through both of them. This is the last slide, so it will be on time. I'll just give you a couple of quick notes here. It's very easy to download ZAP, for example, and point it towards a server. Don't do it. The difference between a cracker and a security tester is permission. So don't do it against somebody else's server. Don't even do it against your own production server. You will probably be unhappy. It's more likely that there are some findings and you will end up ruining something if you do this. And what you need is a production environment, and it's basically the same thing as a staging server, but I want to turn it like this because many people have like this huge 120 machine cluster for their production environment, and yeah, we have this crappy old box in the corner for our staging environment, but that's not the right way to go. What you need is something that is architecturally similar to your production environment, meaning that if you have a load balanced environment in your production, have a load balanced environment in your staging also. You don't have to have the 100 machines. It's enough to have, for example, 3, but you can still test things like dropping a node from the cluster and resuming it and making sure everything works. Proper cloud environment and deployment automation obviously makes this pretty cheap and easy. You should all do it if you already haven't. Then, as I mentioned, browser-based automatic tests are very nice. Road framework is awesome. Use it if you haven't. How many have used Road framework? Surprisingly many. Damn. You feel that. There is a problem with false positive elimination. So many of these tools will give you false positives. I suggest strongly that you tweak their output so that you don't kind of favor specificity over sensitivity. So people will start ignoring the results of these tools if they continuously produce false positives. It's better to have really robust findings rather than everything possible and go through every time. Do we need all this, and is it going to be very expensive? Well, do we need depends on the application. If you're doing a marketing site for a movie, probably you don't really care that much. Just try to use the most recent versions and have a good backup scheme if somebody hacks into your server, and maybe monitor the traffic so that you know that if it starts to participate in a denial of service attack, you'll be aware. But if you work for a large bank, say, and have control of millions of euros or billions of euros of people's capital, it's probably a good idea to do this properly and go through this exercise. As for cost, if you already have a Jenkins server and kind of proper CI setup going, you can pretty much do the basic version of this in a few days. I've done it myself. It's not terribly difficult. The actual time-consuming part is shifting through the false positives and tweaking the tools to do kind of sensible things in your context. That's all. I know this was kind of rapid fire stuff. Hopefully you gained something. I will be available here during the lunch and evening during the sauna session if you have any questions or comments. And thank you, Jani, again. Jani will be here at least for during the lunch. So if you have a question, that's also an opportunity. But thank you.